Hello, everyone. Thanks for joining. Welcome to the first CIIR Talk Series of 2022. It is my pleasure to introduce Urvashi Khandelwal. She's a research scientist in the language team in Google AI. And she got her PhD from Stanford National Language Processing Group, where she was advised by Dan Jurovsky. She's mainly an NLP/machine learning researcher and interested in building interpretable systems that can generalize in and adapt to a range of settings. She has done some amazing work on retrieval augmented or retrieval enhanced models for a number of NLP applications, which I'm pretty sure that you'll find interesting. And her work has received awards, including a Microsoft Research Dissertation Grant in 2020. Without further ado, I'd like to ask Urvashi to talk about generalization through memorization.
Cool. Thank you so much, Hamid, for that nice introduction. Hello, everyone. Thank you so much for having me here to kick off a new year of CIIR talks. So like he mentioned, I'm today going to tell you about my work on generalization through memorization. And while I am at Google now, the work I'm going to tell you about today was all done while I was at Stanford and in collaboration with Facebook. So in recent years, our lives have started to become supplemented by smart tools, especially language tools like translators, writing features like Smart Compose, virtual assistants like Alexa and Siri, and many more. And thanks to deep learning, the NLP systems that power the NLP models that power these systems have never been better. In fact, since about 2018, neural language models have been at the heart of most of our best NLP systems. Now, informally speaking, language modeling is the task of predicting a missing word given the surrounding context words, and using these language models as the foundation of models that perform other tasks has brought us a lot of success. For instance, Google search uses BERT to improve the quality of their search results. Facebook uses XLMR, a large language model trained on 100 languages, to improve their content understanding tools. And this is used, for instance, to detect and remove harmful content like hate speech from their platform. Language models also form the basis of text generation systems like translators and chatbots, where they're used to generate sequences of text word by word. And with the release of GPT-3 and really tons of follow-up work, we found that just by showing these language models a few examples, we can have them perform new tasks that they haven't seen before, like translating English instructions into Unix commands. So without a doubt, neural language models have become the workhorse of most NLP tasks and systems today. And yet, the road ahead is long. Language models aren't perfect, and there remain a number of open challenges in improving them still. One of the biggest and most important challenges in building these models is improving their generalization. So a simple question that we might ask is, do our models always work as we'd expect them to? And the answer is not really. Sometimes they can straight up fail to generalize when given previously unseen inputs. So in this example, a machine translation system is translating food items into celery mildew and cardiomyopathy. So let's take a closer look at what I mean by generalization. Now, the dominant paradigm for building NLP models is to train them to perform a single task learned from a fixed and often single domain training data set. For example, here, translating German news articles into English. And then when we want to evaluate this model, we measure its performance on unseen test data from the same or very similar data distribution. And this provides an indication of how well the model generalizes. Now, in recent years, we found that our models tend to perform quite well in these in-distribution settings. But even in some cases where the train and test data come from the same distribution, the model performance can be inconsistent. For instance, even though our model can seemingly translate German news articles into English, moving to a new language pair can call this ability into question. And this shows that we still stand to improve model generalization. Now, in my work, I've proposed generalization through memorization, where we will improve the model's generalization by saving examples to an external memory. and querying this memory when we're making predictions for test data. And at a high level, this idea relies on the intuition that our models are pretty good at being able to identify whether the test input is similar to some example that was seen during training. And so perhaps the prediction here might be the same as for that previously seen example. This method also improves model interpretability, and I'll show you how later in the talk. Now, when we talk about generalization, we typically look at in distribution performance, but really there's so much more to it because we live in a world that's constantly changing. And as humans, we're pretty good at adapting to those changes. So a natural question to ask is, do the NLP systems that we rely on adapt as well? So back in November 2020, when we had been living in lockdown for about 10 months, I asked Alexa, what do people do for fun these days? And it responded with answers from the web, like travel and spend time with others. This is really misleading. Alexa seemed unaware that we had been living in lockdown for almost a year at that point. It just couldn't adapt. So while adaptation is a much more general idea, in this talk, I'll look at a specific case called domain adaptation. And you can think of this as a form of out of distribution generalization where the train and test data now come from different distributions. As an example of this is when we use our model that was trained to translate news articles to now translate medical texts, which are different from news in terms of content and structure. They belong to a different domain and are generated by a different underlying distribution. And in this setting, we find that our translation model has poor and unreliable performance. It is not able to adapt to different settings and suffers from poor out of distribution generalization. So to address this, in my work, I'm using memorization to make models adapt to different domains by storing domain-specific data, like the medical texts in our example, into the external memory. So really, the main goal of the work I'm presenting here today is to improve generalization of our models, both in and out of distribution. But before we talk about why memorization is a good approach for this, let's recap the current state of neural LMs. So recently it's been shown that current models might be memorizing knowledge in their parameters during training. Is this adequate? This kind of memorization is brittle because when the model parameters are updated, it's unclear how much of the knowledge is preserved and how much gets overwritten. It's also unclear how much we can control what the model memorizes in its parameters. And this is especially important because the model can't just infinitely memorize all knowledge. Its capacity is limited. In addition, because we live in a world that's constantly changing and evolving, every day there are new facts that the model hasn't been trained on, like who won Super Bowl 55 or how has COVID affected our lives. Large language models are unable to adapt to these distributional shifts in data, which in turn hurts their ability to adapt to changing environments. Another limitation is that given present day model architectures and hardware, these models require tremendous amounts of compute to train. So in light of these challenges, in my work, I've proposed generalization through memorization. And I don't mean implicit memorization in the parameters, but explicit memorization of examples. So I'm referring to the process of saving data in an external memory, and when given a test instance, retrieving similar examples to make similar predictions. And while at first it may seem like a bit of a paradox that memorizing can help the model generalize to new situations, it's actually quite a natural approach to be matching new data to similar previously seen examples. And a simple way to illustrate this is the fact that we all know that the phrases Pride and Prejudice was written by and the author of Pride and Prejudice is mean the same thing, even if we don't know about Jane Austen. So why is memorization an interesting approach to study in conjunction with these machine learning models? Well, this approach really draws its inspiration from the widely studied exemplar models proposed in psychology and cognitive science. So these claim that humans categorize information by storing examples for each of the categories, and they make new classification decisions by matching the features of the presented stimuli to the stored exemplars. And before deep learning was widely adopted, these exemplar models had been explored for NLP tasks as well, like morphological tagging, parsing, example-based machine translation. But these models typically involve the use of discrete features, and measuring similarity in these complex feature spaces posed some serious challenges. So in this talk, I hope to convince you that this age-old idea of exemplar models or memorization is particularly interesting to study in conjunction with deep learning models for NLP. So at a high level, what does my proposed version of memorization entail? Recall our train and test setup from before. Well, we're going to build an external data store and save our examples in this data store and then query it when making predictions. Now, building and querying this data store doesn't incur any additional training costs. So memorization is not prohibitive. Any existing model can be used without having to update its parameters. And since this form of memorization is separate from the model's parameters, it gives us control over what information gets saved. So the first key result from my work that I'll show you is that when the data store contains the training data, the data the model was trained on, this method still results in improved generalization, even when the underlying base model is a strong baseline. Next, I'll show you that this model is extremely useful for domain adaptation as well. So recall this setting where the train and test data now come from different distributions. Well, this model can be adapted to multiple new domains by simply switching out what gets stored in the data store without having to train on that data. Another benefit of memorization that I'll highlight is that by querying the data store of examples, the model's predictions become more interpretable because they can now be traced back to the specific examples that were used for making the prediction. At this point, I'd also like to note that memorization and scaling models by adding trainable parameters are not mutually exclusive approaches, but the behaviors of billion and trillion parameter models are still relatively understudied. So we do need to still establish a clear relationship between the size of the model and the use of a non-parametric memory in those cases. Okay, now let's dig into specific details of the nearest neighbor language model and the nearest neighbor machine translation model to understand how well this approach works to improve generalization for these tasks. So I'll first start by defining the neural autoregressive language model. These models typically take as input some prior context, like Tony Stark lives in, denoted by C sub t. And the model F maps this to a high dimensional representation, which is then used to estimate a probability distribution for the target token W sub t. And in this talk, this type of an autoregressive model is the basis for all our experiments. And model performance is evaluated using perplexity, which measures how well the model can predict the test data. And lower values of perplexity indicate a better model. Okay, now let's investigate the hypothesis that memorizing this prior context will improve language model generalization. And to verify this hypothesis, we propose nearest neighbor language models, or KNNLM, which involves interpolating a pre-trained language model with a nearest neighbor's retrieval component without any additional training. And at this point, let me remind you of the key intuition that's powering this whole enterprise, being able to identify that two contexts like Tony Stark resides in and Tony Stark lives in mean the same thing, even if you don't know where he lives. So keeping this intuition in mind, let's walk through the details of KNNLM with an example. So we first start by feeding our test context, which is denoted by X here. So I'm going to use X to denote the test context, and C will denote the memorized contexts. So we feed this test context to the language model, which outputs a distribution for the next word, and also a high dimensional representation of that context, f of X. And this representation is used to query the nearest neighbor's data store, which is just a collection of keys and values that was constructed offline. Let's quickly see how that was done. So we were given some text collection, which can be the training data or really any other data set. And we did a forward pass over each of the examples using our pre-trained LM. So we computed f of C for every single one. And this gives us context representations for each example, which are stored as the keys in our data store. and the corresponding targets are stored as the values. And note that the same value can appear multiple times in the data store because we're saving every single occurrence of it along with the corresponding context representation. And that's the final data store that we're using during inference. So getting back to our test context, recall that we have this query, which is just the test context representation. And we're going to compute distances between it and a subset of the relevant keys from our data store. Then we'll prune that list and keep only the top k nearest neighbors. Next, we normalize the distances to get a probability distribution and aggregate over multiple occurrences of the same value to get the KNN distribution. And the last step is to just interpolate the LM and KNN components using a manually tuned interpolation parameter lambda to get the final KNN LM distribution. And remember that all of this was done without any additional training of the model's parameters. And that's basically how the model works. A few key details for our experimental setup. So our base language model is a transformer LM, which was the near state of the art at the time. And our data store is implemented using FICE, which is an open source library for fast and efficient similarity search in high dimensional spaces. Okay, now let's see how effective our model is. So the first experiment is designed to test whether KNN-LM improves generalization at all. And for this, we use the Wikitext 103 data, which is a standard language modeling benchmark. It's 103 million tokens. And the state-of-the-art perplexity at the time, using only the training data provided, was 17.4. And our base LM is a bit worse at 18.65. But providing the base LM with the nearest neighbors data store that contains only the training data provided improves perplexity to 16.12, which was also the new state of the art at the time. Now, this large boost from using KNN-LM without any additional training and without any additional data is really quite surprising. It shows us that simply memorizing the training data can help improve LM generalization. So here's an example that KNN-LM was particularly effective for. The input context is talking about Joseph Warbrick, a rugby player from New Zealand, and how he had a significant impact on the development of the game there. And the true target word here is development. And the language model places a pretty low probability mass on this token. And here are some of the neighbors retrieved by KNN-LM. The top neighbor is also talking about Warbrick and New Zealand rugby, and the target is development with almost all of the probability mass. And this shows us that KNN-LM is retrieving examples using a combination of a variety of features, both local contextual features as well as global, more topical features. All right, so given this improvement in LM generalization, we wanted to understand if adding data to the data store that the model wasn't trained on, but comes from the same distribution can help as well. So for this, we train a model on 3 billion tokens of Wikipedia and another one on 100 million token subset. So in this setup, we're controlling for the number of trainable parameters. So both of these models have the same capacity. And performance of the model trained on less data is unsurprisingly worse. But now, instead of increasing capacity by adding trainable parameters, we add capacity in the form of a data store. And giving the 100 million token model all 3 billion tokens in a data store improves performance beyond training that same model on those 3 billion tokens. And so this shows us that retrieving nearest neighbors from the corpus can actually outperform training on it when the number of trainable parameters is restricted. And in this case, KNN-LM has scaled to a corpus that's 30 times bigger without any additional training. So given these improvements in LM generalization, an actual question that arises is, well, how general of an approach is memorization? And in order to verify its generality, we propose nearest neighbor machine translation, or KNN-MT, where we interpolate a pre-trained machine translation model with a nearest neighbors retrieval component, still without any additional training. Now to better understand how KNN-MT works, let's first take a look at what the base pre-trained MT model looks like. So a machine translation model typically takes as input some sequence in a source language like French, and outputs its translation in some target language like English. And the input is typically processed by an encoder, and the translation is generated by a decoder. Now, the details of the model here aren't too important. And in fact, the decoder is basically a language model with a few minor differences that I won't get into. But a consequence of this connection is that CAN-NMT is also very similar to CAN-NLM with a few minor differences. And the only difference that I do want to highlight is that the representations that we use as keys for our data store, they're now conditioned on both the input sequence in the source language as well as the prior context in the target language. So here's an example to show you what I mean. We start by saving tokens from the translated sequence. So the first one that gets added to the data store is this underlined word pride. And its context representation depends only on the input sequence in the source language because there is no prior context yet. But after the first one, every representation is now conditioned on both the input as well as the prior context. And one by one, we save all of the tokens from the target translated sequence into our data store, along with their corresponding representations. So given this setup, you can see that the data store only contains values from the target language, and we only condition on the source language implicitly via the representations. Okay, now let's take a look at some translation experiments where we'll now evaluate our model using the standard MT metric BLUE. So first, we want to know if CAN-NMT is effective at improving generalization at all, just like CAN-NLM was. So in this setting, we use a strong German-English translation model and are going to memorize 770 million key value pairs of news data. But the base model, apart from itself being trained on all of this data, it was also trained on millions of artificial translation examples generated using a technique called back translation, making this a very competitive base model. But even so, memorizing training data does improve performance by about 1.5 BLUE. And this is a very surprising and a very large improvement for such a strong base model, especially given the fact that there's no additional training and no additional data. So given this improvement in performance, we wanted to understand if CAN-NMT can help a model trained on many different translation tasks become a specialist on a specific translation task given at test time. So let me explain what I mean. A multilingual machine translation model is trained to translate to and from many different language pairs. And in fact, in our study, our model was trained on hundreds of such language pairs with automatically mined data from the web. And so training a single multilingual model on all these language pairs means that the information learned can then be transferred across different languages to then improve the overall translation performance. But typically at test time, we're mostly given an input in just a single source language and typically have to translate it to just a single target language. Is it possible then to make the multilingual model particularly effective for that one language pair that we care about at test time? So to verify this hypothesis, we used CAN-NMT with the multilingual model and provided just language-specific data stores. So in this way, we're still getting the benefits of transfer from training the multilingual model while focusing on the specific language pair that we care about. You can think of this as task specialization, where the model is trained to perform many different tasks, and the nearest neighbor component helps the model to especially adapt to the specific task at hand. Now let's see whether task specialization works. So here we have performance from our base multilingual MT model on 3 language pairs. And by using task specialization through CAN-NMT, we get pretty large improvements in performance. In our paper, we've provided about results for about 17 language pairs with an average improvement of 1.4 BLUE, and I've shown just the largest improvements here. Now in this setting, we do have access to lots of automatically collected data. And while the data stores aren't this big for all of the language pairs, we did want to understand the effect of the size of the data store on performance. And what we found is in some cases, even where the full data store contains billions of examples, using just a fraction of the data can improve, result in large improvements in performance. This raises a pretty interesting question about what kinds of data account for the largest improvements when using memorization. And I think that's a really interesting question we should explore in the future. So another point to note is that in our automatically mined data, the highest amount and the highest quality of data that we have is for the English language. And this had us wondering, well, can we use the data translated from English to help with translation performance in language pairs that don't include any English? So for example, if we're translating from German to Japanese, can we query the data store containing English to Japanese translated data? This idea is related to a method called pivoting, and it's usually pretty helpful for languages that, for rare languages that don't include as much data. And remember that we can do this kind of cross-lingual retrieval because the data store contains values only from the target language. And so the conditioning on the source language is implicit via the representations. Okay, so to test this idea, we designed an experiment where we use only the English-Japanese data store and evaluate performance for German and Ukrainian translating into Japanese. And we find that using just the English source data, we get large improvements in translation performance for these language pairs that don't include English. And this shows us that transfer across languages from training a multilingual model can actually make cross-lingual retrieval really effective as well. Okay, so far I've shown you that memorization is really quite effective for improving generalization. And in fact, it can scale the model to larger data sets and help with task specialization, which are just variations of the original generalization setup. But in the real world, inputs to the model won't always belong to the same distribution as the data it was trained on. And for this reason, we want to understand if memorization can help the model adapt to inputs from different distributions, like different domains, without additional training. So the hypothesis here is that memorizing domain-specific data should make the underlying model effective in new domains. And to verify this hypothesis, we designed an experiment for language models where the model is trained on Wikipedia articles and it must adapt to the domain of books. Now, a model trained on 3 billion tokens of Wikipedia has a much higher perplexity on the domain of books compared to the in-domain model. But giving it a data store containing in-domain data causes perplexity to improve by about 14 points from 34 to 20. That's a large improvement. And this shows that a single language model can be useful in multiple domains by simply adding a domain-specific data store without any in-domain training. We designed a similar experiment for the machine translation setting. For this one, we're using the German-English translation model that was trained on news from before, and we're going to evaluate it on medical data. The Haruni and Goldberg in-domain model provides the state-of-the-art number at the time. And as you can see, the news model has much worse performance on this medical data compared to the in-domain model. But once again, we find that adding medical texts to the data store improves the model's performance by over 14 points without training on that data. And similarly, we observed a 16-point improvement for the legal domain. And for this one, we were even able to establish a new state-of-the-art without any in-domain training. And so this shows that in addition to improving generalization in a variety of settings, memorization also allows out-of-distribution generalization, which in this case is domain adaptation. Now, at this point, I want to highlight one last important property of memorization, which is that it adds interpretability to the model's predictions. So if we were to generate entire translations using just nearest neighbor retrieval without interpolating with the base model, then we could see exactly which examples from the data store are responsible for each token that's being generated. So here's an example with a German input that's been translated as, in doing so, it seems as if Erdogan has tamed the, and the model needs to generate the next token. And here are the top 3 examples that the model relies on for generating the word military. All of these contexts match the local context tamed the military in both German and English. And they're also topically pretty relevant. But they vary in the longer range context. Only the first one is talking about Erdogan, while the others talk about different leaders in different nations. So in this way, looking at the retrieved examples can help us understand the model's behavior and the model's predictions, and perhaps how we want them to change, especially in cases where models produce biased behavior. And this shows that in addition to improving generalization both in and out of distribution, memorization also adds interpretability to the model's predictions. All right, and before concluding, I just want to share a final thought on what we know about why memorization is working in our favor. So qualitatively, by looking at a few examples, we noticed that CAN-NLM seems to be particularly helpful for predicting rare patterns like factual knowledge or names. An example is Georges Bizet is the composer of the opera Carmen. So in these cases, it suggests that it might be easier for the model to map train and test examples to contexts to similar representations, rather than trying to memorize the next word in the parameters, which you might recall is precisely the intuition that we started with today. All right, and then before discussing what's next, let's quickly recap the progress we've made towards our goal today. So first, we saw that memorizing prior context improves model generalization without adding any training costs. And it does so in a number of settings, including scaling the model to larger data sets and facilitating task specialization. Then we saw that memorization is also really effective for improving out of distribution generalization, and specifically it allows domain adaptation. And finally, we noted that beyond generalization, memorization also adds interpretability to our models. So now I'll conclude with some ideas for moving forward, given these findings. First, CAN-NLM is quite effective, but it does add some amount of latency during inference. Depending on the size of the index, decoding speed can be slowed down by up to 1 to 2 orders of magnitude. So we need to explore ways of making it more efficient by more intelligently deciding what examples to store in the data store, rather than storing all examples in a brute force manner. And some recent work from He et al. Has already started to explore this. In addition, from a systems perspective, there's quite a lot of research going on in trying to make approximate nearest neighbor search faster. And the modularity of CAN-NLM sort of makes it exceedingly simple to swap out the retrieval system for more creative and efficient ones. Next, we know that memorization is effective, but we still don't quite understand why it's causing such large improvements in generalization. Is it the diversity of the contexts in the data store, or do only the long tail contexts help? Is the memorization reinforcing what the model has learned in its parameters, or is the information stored in the parameters and that stored in the data store somewhat separable? I think asking such questions, especially as we try to understand how trustworthy these models are, is quite important. But apart from trustworthiness, these questions can also inform our decisions about scale. So scaling the size of the data store versus scaling the size of the parametric model. Can we achieve competitive performance between a billion parameter model and a smaller model coupled with a large non-parametric memory? So these are just some of the interesting questions that I think we can explore moving forward. I'm very excited for what's yet to come in research in the space of non-parametric and semi-parametric approaches. But yeah, with that, I'd like to thank my collaborators from Stanford and Facebook for all their help and support. And thank you all for listening.
Great, thank you, Urvashi. It's very, very interesting and thought-provoking talk. I really appreciate it. So we have a number of questions in the chat. So
okay.
In the first question, Arbaz is asking, how exactly do you build the key value pairs of the data store in your CAN-NLM experiments?
So I think I did. I'm not sure if this came up before I like walked through the construction of the data store. But like the idea is generally that we're given some text collection and we do a forward pass over the corpus with our language model. And extracts the context representations and the corresponding target word. And the context representation is what's stored as the key, because we're doing the similarity search in high dimensional representation space, and the corresponding targets for those representations are the values.
Okay.
I'm not sure if that answers the question, or if there was a more specific question about it.
Please, Arbaz, please ask your question in the chat if you're not convinced. I'm moving forward to the second question from Hong. Hong asked, do you use pre-trained models on Wikipedia? So in this case, the model has already seen all the data in Wikipedia. Would you evaluate the KNN model outside Wikipedia? And then she also mentioned that after your domain adaptation results, she mentioned that your later experiments answered the question. But is there anything else you wanted to add?
I guess I do want to add that our we did sanity check all of our in distribution experiments also. So the data that's used for training and the data that's used in the data store is all separate from the evaluation sets. So the def set and the test sets are held out. Yeah, so we're never, there's no explicit leakage of Wikipedia documents between the train and the test setup.
Okay, sounds good. And we have one question from Jeremy, who asks about temporal adaptation. So he asked, would the domain adaptation approach also work for the example you gave at the beginning, which was, Alexa, what do people do for fun? That is, if you had an old model trained 2 years ago.
People do all sorts of things.
Alexa, just go off.
That is, if you had an old model trained 2 years ago and new memorized examples that had been created since the beginning of the pandemic, would it work?
I think the fact that with the data store, we have such good control over what we store in the data store, the hope is that we would be able to adapt to these temporal distributional shifts in data by just updating the data store without having to retrain on the model. Because the distribution of the language, I think, changes very, very gradually over like centuries, but the new facts that are being generated every day, we can sort of update the data store on the fly with these new facts. And hopefully, given that the distribution of language remains the same, we should still be able to have good retrieval results.
Okay, makes sense. And his follow-up question is, okay, if it works, then how might you would know when to use the newer information and when to use the older information during the retrieval?
That's a good question. I guess we would have to probably start by maybe aggregating all of the information in the data store and seeing how well the model is at sort of being able to retrieve the correct information. I think we might definitely run into some issues with examples like, oh, the president in 2015 versus the president in 2021. Those kinds of differences that are not maybe including the time stamped data. I think we might still run into issues and need to find better ways of being able to add more structure to that data, so we know exactly what time period Abraham Lincoln being president versus Obama being president, how that that maps out in our structured information. I think we need that structure in the data.
Okay, sounds good. Let's move on to the next question from Dick. Dick asks, it seems to me that you are using pre-trained LMs as powerful feature extractors, which have great generalizability proved by your experiments. Mm-hmm. Could we make pre-trained LMs learn to use your external memorization so that they may better utilize that memorization?
Yeah, I think so. I think sort of fine-tuning the model with the retrieval in the loop, it seems like a pretty promising direction. I think certainly one of the attractive features of our approach is that it doesn't add a lot of well, it doesn't add any training costs, and so it's kind of almost like a zero-shot approach. So I think I personally would be very curious to see how much value the fine-tuning adds to the generalizability of the representations and the retrieval. So I think, yeah, I think that would be a pretty fun thing to try. I'm not aware of anyone who's tried that yet.
Okay, thank you. Jeremy also asked another follow-up question. Would this be a way of reducing LM bias? For example, if you memorize debiased information and update it as new instances were found?
I think like it's a pretty compelling hypothesis, right? I think like running these experiments would definitely tell us a lot about how much we can control. Like certainly when we're only using the retrieval and not interpolating with the base model, retrieving from the data store gives us control over what kinds of examples the model could possibly retrieve, and so what kinds of outputs it could possibly generate. But then I think there is also a trade-off to consider where when we purely retrieve from the model, we maybe start to lose the generalizability of the language, the model itself, the underlying model itself, in cases where the desirable information is maybe not present in the data store, but we can still expect the model to generalize. So there are trade-offs, I think, there to be considered. So would definitely be an interesting experiment to understand if we can actually control the bias with the data store. But I think it's a compelling hypothesis for sure.
Okay, thank you. The next question is from Arbaz again, who asked the first question. I think my question was misinterpreted. Let me ask it through an example. Consider the sequence Arbaz and Hitesh are friends. What is the key and what is the value for the above sentence?
So there would be a number of keys and values. We basically we run through the entire corpus and have a sliding window where we have some tokens that are used as a prior context and the following. So it's an autoregressive model. So we always have leftward prior context. So maybe in this case, Urvashi and Hitesh, and then the target for that particular prior context would be R. And then for the prior context, Urvashi and Hitesh R, it might be, the target would be friends. And we're storing the context representation, of course, not the tokens.
Mm-hmm. Great, that's clear, thank you. Another question comes in just. So Nigel is asking, is the computational downside using a retrieval component significant?
Yeah, it can be. So it definitely depends on the size of the index. And for the indices that contain on the order of billions of examples, the slowdown can be about like 2 orders of magnitude in the decoding speed. So it is quite significant, but given the performance improvements being so large, I think it definitely warrants a lot of investment in trying to figure out how to make it faster.
Mm-hmm. And Hitesh is asking, do we retrieve for every token we generate?
Yeah, that's what we've been doing in our work. I think there's been some follow-up work from Graham Newbigg's lab that where they basically explored using an adaptive interpolation parameter, so they don't necessarily retrieve at every time step. So I would suggest checking out that paper. It's called Efficient Nearest Neighbor Language Models from Graham Newbigg's work. Okay,
thank you. Mm-hmm. So there is no more questions in the chat. Since we have time, I'm gonna ask one question that I have myself. Mm-hmm. So in the beginning, we'll start with some motivations that we have large language models, and we know that they do memorization extensively. Mm-hmm. Do you think that do you think that's possible to disentangle memorization and generalization? So we have a much smaller model that only learns to generalize, and then put everything that's related to memorization to a memory, and we retrieval over that.
Right. Yeah, I think that's one that I hope is true, but I think I would like to run the experiment before claiming one or the other. Just because it seems like for maybe the long tail of the contexts that might be true. But maybe for given the Zipfian distribution, like for the middle of the context, for the middle part of the distribution, there might be more overlap between the two, and so it would be harder to disentangle. So I think like a simple way to do this is just sort of like run the experiment where we vary the size of the model, or hold the size of the model fixed, and then like grow the size of the data store, and then like start to vary the size of the model along with that, and see how much performance changes. Can we find a point where making the model larger doesn't add anything to the model's generalization capabilities because the data store is sufficient to compensate for it?
Okay, yeah, makes sense. Thank you. Again, thank you. I really appreciate it. It was a really interesting talk.
Thank you.
I personally really enjoyed it. And I think I also have one announcement for the audience. We normally have this CIIR talk series every other week, but the next time, which is 2 weeks from now, is an exception because it's right before the CIIR deadline, and the majority of the audience would be busy with that. So there will be no talk in January anymore. So I'll see you all 4 weeks from now. Thanks again, Urvashi. I really appreciate it. And I think I'll talk to you at 2:30 in the other Zoom meeting.
All right, thanks. Thanks, everyone.
Bye.